All right, so we're going to talk here about graph transformations on quadratics, and it's important that as you watch this video that you have your guided notes to use alongside it, and that would be these notes that you see here. And what we're looking at is what happens to the graph of a parabola, of a quadratic function, when you do certain things to it. Now we're going to use Desmos as a guide for looking at that. But first, the concept of a parent graph. The parent graph is the graph that's the most basic of a family of functions. It is the graph, as you can see here, that doesn't have a number added to or multiplied to. It's just y equals x squared in this case, as opposed to these that have numbers there. So I've looked at Desmos, and I have y equals x squared graphed here. And what I'd like to explore is what happens when you do certain things to it. And that's what the notes are for here. So what I've prepared is a little slider here on Desmos to show you the effect of doing certain things to y equals x squared. So what I can do is come down on this screen and say y equals x squared plus 3. And in green you can see that we have the new function, that is in green x squared plus 3 versus the parent. And you would ask yourself, how do they vary? Well, you can see they're basically the same width. It's just that the green graph moved up 3 units from where the original one was. So what you would do on your notes here, you would say, where it says what happened, you would write up 3 or something to that effect. And notice the description, add on the outside, that is not within the parentheses like you would see down here. There's a tendency for it to go up. The second row here that you fill in, ask what happens if you subtract on the outside. So let's explore that. I could simply change this plus to a minus, and you see again, if I zoom out, it's really the same width. It's just that the graph went down 3 units. This vertex, what we call this turnaround point, went down here. So if you subtract on the outside of a function, you go down. If you add on the outside of a function, you go up. So here you would say it goes down 3. Now let me show my slider here to illustrate that. So if I go to my other screen, notice this little setup here. The outside number is the k here. So what I'm going to do is change this k. Right now it's at 0, which is where the parent is. But as I move the slider such that k becomes a positive number, notice that the graph is going up. So what this is doing is saying, okay, what if we take this and we add it to, in this case, 4.4. It goes up 4.4 units. So if I add on the outside, you're going up. If I go the other way, and where it becomes negative, you see it's now below the x-axis. So I'm going to reset that back to 0. All right, let's now go to our other graph and ask the question, what happens if I add or subtract on the inside? Well, first let's add on the inside. So I'm going to go like this. I'm going to put a parenthesis, x plus 3 raised to the second power. And notice that if I add on the inside, it appears to be twin graphs, except the green is now to the left of the red. And that may be a little surprising. Adding here actually goes left. You would associate plus with a with going to the right or in the positive direction. But as we said earlier with the vertex, you change the sign on the inside. If you were to put a negative 3 where x is, it would cancel out and make a 0. So if you add on the inside, you go to the left. So on here, on this part here of the slide, if you add on the inside, you're going to go to the left. So you'd write left 3 here. If you subtract on the inside, not hard to figure out, I'm sure you're already thinking this, you're going to go to the right. So let's illustrate that. Okay, so notice that I go right here. It's the same graph. The width was not affected. I just go to the right. Okay. So on this fourth row, you would say goes right 3. Let's illustrate that with our slider. All right, so this time if you look again at our parent, the inside number is the h. So if I come down here and only affect h, look what happens when I make it positive. The graph, watch the graph. It's moving to the left. However, if I go such that h is negative, okay, so now you're subtracting on the inside, the graph is going to the right. So you can see that animation there. And you would be able to just play with this and see what happens as I move. Notice it takes plus or minus to make a graph move. I can actually do both. I can go up and across. So notice as the graph moves, as h and k changes, it goes up and down, right and left as it goes. So let me reset these each to 0. Let's explore what happens when I multiply by a number. Okay, so that would be like this a value here. So I'm going to go back to my other screen. I'm going to start to explore about what if I multiply by a number larger than 1, a positive number larger than 1, like 2x squared. Okay, now here obviously the difference is it didn't move. The vertex is still at the origin. What changed was it is now more narrow. We actually call that a vertical stretch. So what you would do on your notes here on page 2 shows the parent again. And there are these little graphs which may be hard to see on here but easier to see on your notes. If you multiply by a positive number larger than 1, in this case it was 3, so maybe I should make it 3, it makes it more narrow. Okay, the larger the number, the more narrow it gets. So I would write narrow here, and I also would write the word vertical stretch, which is indicating that you grab it, you sort of grab it and pull up on it, making it more narrow. This next row says, what if I multiply by a positive number smaller than 1? That's a positive number smaller than 1. It's certainly possible to do that. We're talking about like numbers like 1/2, or I think it was 1/3 on the sheet there. And as you may have predicted, again, the red parent has not changed at all here. If you multiply by a number less than 1, though still positive, it is now wider than this graph here. Okay? And that would work if it were a fraction or a decimal. 0.4, for example, is still wider. On this sheet, you would say wider, and you would write the words either vertical shrink or vertical stretch. Excuse me, vertical shrink or vertical compression. Stretch is more narrow. Okay, so here you would say either vertical shrink or vertical compression for the wider part. Okay, again, stretch is more narrow. The last thing that we're going to explore is what happens if you multiply by negative. Now, a quick note here, when it comes to stretch versus shrink, that is narrow versus wide, the negative doesn't count. So if I have a number like -2, for example, we only look at the 2 to determine stretch versus shrink. But if I make it negative, let's just make it -1 to see what happens here. Okay, and the graph gets reflected. That gets reflected in the x-axis. That is flipped over the x-axis. If I put a number larger than 1, it's also going to make it more narrow. As you can see there, make it 22, it got really narrow. But if I make it less than 1, like 0.5, it's going to get wider. So the negative here makes it flip upside down. It's the size of the number, regardless of the negative, that determines if it stretches or shrinks. Okay, so to summarize that, here you put vertical stretch, narrow. Here you put either vertical shrink or vertical compression, wider. And here you would say reflected in the x-axis. Or you could write upside down. That's the influence of a negative. All right, so to finish, I'm going to look at my animation. And this time we're going to mess with A here. And watch what happens to the graph as I get a number larger than 1. That is, you're multiplying by a number larger than 1. Watch it get more narrow. Okay, the bigger it gets, the more narrow it gets. But if I go less than 1, let me be careful here. So I go less than 1, notice it's beginning to get wider. Okay, it's only going by increments of tenths here. Okay, but as soon as I flip to negative, we expect it to go upside down. And there it goes. And as it gets more and more negative, it will begin to thin, as you can see it there. So those animations are a great way of looking at and sort of visually seeing the influence of those graphs. So please pause this video as needed, fill in your guided notes, and then use that to work our assignment.